Recording. Sure. Let's do it. Hey, today we're going to do some probability. So those of us in class, those of us not in class, probability. Now I say this, we're not spending a lot of time. Really today is going to be the main day of probability. Talk about some main features here. This is going to be enough information to make you dangerous in recognizing things, especially like on the ACT. At least have an understanding of what to do with it, right? But please note that there's a whole world more of probability, right? And probability can get really confusing because there's a lot of special quirks when you get into just the way things are asked here. So my plan is not to dive into all the quirks of it, but just to look at the basics of it. So some of you might look at this and say, Mr. Roy, this is a little too easy, but I think you'll pick up some things that are going to be helpful and maybe important today. So with all this being said, though, right? And again, ACT, we all saw probability on the ACT, did we not? You should have, because we had it. When we say, what's the probability of something happening, what are we really asking ourselves? What is this? Whoa. Clicking on stuff, Mr. Roy. It picks up more. So what's the probability it's going to rain today? What are we saying?
It's a 50% chance. It either does or doesn't happen.
Now there's two different kinds of, Michael said this, right? And this is true about most everything. Michael said there's a 50% chance it's going to rain today. Either it will or it won't. Is that not true about everything in life? Either it is or it is not going to happen. Now there's two words for this. This is called theoretical probability, right? Is what that's called. The weather forecasters, even though they might feel like that's how they are, they're half the time right, half the time wrong. We usually go by something that's called empirical probability, which is built upon other formulas and other things that go with it. But probability, though, what are we really saying, though? The probability it's going to rain, what's that really saying?
What are the odds?
Not the odds. Be careful. Odds is a trickier word. That means something different. It's a chance of something happening out of what? It's a chance of something happening. It's a ratio of these that measures the chance of something happening. When I say the word ratio, you should go straight to what? Go straight to the F word, fractions.
Which make us scared.
Whoa, Mr. Ryan.
And fractions, this is what a probability always is. It's comparing two things. It's comparing the number of successes, so how many times it could happen, whatever I'm trying to find the probability for, over all the total possible outcomes. And we've spent last week a little bit on Wednesday, Thursday. We spent time finding ways to get total possible outcomes, ways to count. We're going to use those today to find the number of successful events over the number of total events of what that might be. But this is always a ratio. If this is a ratio, then what's that mean about my answers all the time?
They'll be less than 1.
My answers are going to be less than 1 and greater than what? 0. And so if you had the smallest probability is a 0 probability, what's that mean?
It will not happen.
It's not going to happen at all. The biggest probability can be is like 100%, which is a probability of 1. And so these are these kind of the extremes you can be at. So the probability of an event happening is always between 0 and 1. 1 means that it's guaranteed to happen. So if you have a probability of 1, that's like saying it's 100%. It's going to happen. A probability of 0, though, means that it's impossible. It cannot happen. There's zero successes out of whatever total number of possibilities that there might be. Now I think we're all under the age of 18, are we not? No, we're not. Some of us are 18. We're under the age of 18, right? So I say this because we cannot gamble, right? True? Legally?
Well, it's Nebraska, we can't do it anyway.
I know, but I'm just saying this though, right?
Even if we were 18.
One thing that in the world of gambling, you see a lot of, not probability though, right? So when you read the read the paper and stuff and go to Vegas and stuff. It's not about probability on like betting on sports games and stuff like that or betting on horses. It's all about the, Owen said this word before, it's the odds. And I want you to understand, odds are different. Not that we're going to deal with any odds necessarily today, because I told you we're going to keep this kind of simple, but you know what odds are actually measuring? It's a ratio. It's the chances of, it's the successes, so the number of successes. But it's not over the total, like this is over the total, it's over the number of failures. And so your odds is a different measurement, right? So my wife, God love her, she always, when she's wanting to talk about probability, she'll say, hey, the odds of this happening is this. I'm like, no, that's not probability. Probability is, success is over the total, but she uses the word odds a lot to represent probability, because the two are very similar and stuff. They're a ratio of two things. It's like the Cubs, for instance, right? What's the probability the Cubs are going to win the World Series this year?
0.
Well, there's how many teams are in the playoffs? Here, right? We go this way.
There's 16.
Baseball is my.
There's 16 teams in the playoffs, right? So the probability of the Cubs winning, right? Let's just go if they're all equal. Cubs winning.
Well, this year, there's 16.
Yeah, that's the thing.
This year, I know
why
this
they
year.
use
Let's
those.
just go this year. There's one successful outcome, right? Over what are the total possible outcomes? 16, right? That's their probability. If I said what are the odds of the Cubs winning? Odds. A lot less.
Yeah, a lot less.
So the odds of the Cubs winning would be what? How many successful outcomes are there? One out of how many failures? There's 15, right? There's 15 other teams that could win it. So they have a 1 in 15 chance, kind of, or the odds are 1, I shouldn't say 1 out of 15, but 1 to 15 are the odds for it, right?
So how do they actually calculate teams, like a perfect representation of the odds of a team winning?
Oh,
This is
well,
where
they-
there's,
I know-
this is where
I know
computers
that.
come into play. This is where, again, this is called empirical probability. They take all these formulas and stuff and say, hey, like Nebraska, for instance, the probability or the odds of them winning the national championship in football this year is 1 in 200, 1 to 200. There's one successful outcome over the,
Our Big Ten odds.
200 failures.
Big Ten odds right now are 1 in 40.
I know, I'm saying national championship. I read that somewhere that's like 1 in 200 for betting purposes. They use that. But they take all these other formulas into account, and someone sets those odds, is what it is. Usually it's Vegas that does it, and Vegas never loses in the long term, right? Make sense or not make sense? Keep going then with Mr. Lloyd. Keep going. Write these down. Try these.
They always keep the odds up. I don't know why.
You got a coin. You're gonna see a lot of coins today. We're gonna play a lot of cards today. So coins and cards are gonna come up. You toss a coin 3 times, right? So I have a coin, heads and tails, right? Normal coin. I don't have any money on me here, right? What's the probability of getting exactly 3 heads? And
I can't tell you. I'm trying to throw this.
and even with this, I'm gonna go a little farther here and throw some other scenarios up here. And here's where I need to write on the smartboard here, since this is the only thing recording. So think of a coin, I flip it in the air 3 separate times, right? Only 3 times. What's the probability of getting exactly 3 heads every single time? Head, a head, and a head. And the way we write this in a moment, we're gonna write probability. We'll put a P for probability, and like in this case, I wanna have a head, and a head. So those are my 3 outcomes that I desire, right? That's what I want to have happen, a head. Versus 2, I want to have at least 2 heads, so there's a lot of different options there, whether I get a head, and a tail, a head, a tail, head, tail, head, but what do I need to know, though, to do this, though?
The chances of getting 1 head.
The chance of getting 1 head, but I need to know over the what, though? Once again, what's the probability, though? Over the... Can I find what the total number possible is? Sometimes you see this, you'll hear this word, and actually I think the first couple of questions I'm going to ask you to do for practice, you're going to see this word right here, and they use this word sample space. I don't know if you remember this from, and the sample space is all the possible outcomes possible, right? In something like this is possible to list out all the possibilities. Like some events are way too big. You don't want to write all the possible outcomes out because they're way too large. Do you think you could write out all the possible outcomes here? And how many possible outcomes are there if I flip a coin 3 times?
tail.
Cause I could go head or tail, right? The first toss, so this is the first toss, head or tail. But then what can I do from my head and what can happen after the first toss? So the second toss, what's my outcome there again? So if I flip a head, the next time it could be a head or it could be a tail. Likewise, if I flip a tail, the next time it could be a head or it could be a tail.
Oh, I remember these.
This is kind of this tree diagram. You may remember these. What's my next third outcome? I could be what again? Or I could have again a head or a tail if I flip the tail that time. Or if I have here again, I have a head or a tail. You see what I'm doing though? Yes? Again, what are the possible outcomes though? And you probably didn't even have to draw this, but if I had to list this out, you could have a what? You could have a, if I choose the top route, I could have a head. Or I could have a head. So this is called your sample space. These are all the possible outcomes is what this is making for us. And sometimes drawing it out, which I know some of us are grumbling about this, I could go what's my next one? Head, tail, head. Or I could go head, tail. My last set here would be tail, head, tail, head, tail. Or tail, head. Or finally, last but not least, tail. How many outcomes are there though? If you look at all these sets, there's 8. And you actually could have figured this out before we even started.
Did I not?
No, you didn't.
What? I was like, oh.
That sounds like 3.
You said
Yeah,
that sounded, that's why I
I
thought you
swear to
said
God, I said
6
8.
earlier when you're like, what's the total
I
number of
said
outcomes?
8. I
I
swear to
thought
God, I
you
said
said
8.
6.
Oh, okay.
8.
Now, why does it make sense to get 8 though? Can anybody think logically? Because
Because 2 times 2 times 2.
if you have, again, go back to the ways of counting, right? First time you toss, how many outcomes the first time? You have 2 options. The next time you toss, you have 2 options. The third time you toss, you have 2 options. That's a total of 8 outcomes. The sample space shows you that, but this is still what we call the fundamental counting principle. You can still count every single time what they are. The nice thing though about this though is, if I know this, can I move, Mr. Roy, can I move these down? I can. I will here. What's the probability of getting exactly 3 heads then? How many times can I get 3 heads? There's only one time that happens out of what? So my probability, I'll write it as a fraction, is 1 out of 1/8. And that's between 0 and 1. Now at least 2 heads. What's at least 2 heads mean? I could have 3, but at least 2. So count the number of ways. Look at your sample space. How many ways can I have at least 2? 1, 2, 3, 4, 4. So there's going to be 4 out of 8, which again, if this is what I get for an answer, I would prefer that you would reduce it and write it as a reduced fraction of 1/2. So the probability.
Without writing all the sample spaces.
50%.
There's a formula for it, but you don't want to know. It's more complicated than what it needs to be. Like for this case, it'd be easier just to write it out. The words, and this is where we're not going to get too great into, is the word at least is kind of a more complicated way. I don't like that answer, but I'm going to avoid going down that road for the sake of the time and focus you want.
Yeah.
But there is a formula that you could do it without writing it out. No heads.
1 out of 8.
There's only one that's no heads, and that's the tails. And so again, 1 out of 8. So simple things, you could write them out if you had to. And I think they're going to ask you for one question or two to write out the sample space. That's what it looks like. But it's easy to see the outcomes then with it, right? Keep rolling with Mr. Roy. Keep rolling. Simple things real fast. Simple things. I got to say this because guess what happens? Some of us, we maybe don't know what these things are, right? So I've learned too much in my life. People don't. We flip coins, right? Hopefully.
Are you trying to tell us what a coin is?
Well, I'm just going to I should have maybe started with this though, but a coin usually has a head and a tail. So if I say what's the probability of getting a head? 1 out of 2 options, right? Because there's 2 there. What about a die though? We all know what a die is. A standard die has how many sides? I should be specific here. I should maybe say 6-sided. So that's like, it's like flipping a cube, right? And what numbers are on a cube? 1 out of 6. So what's the probability of getting a 4 though? 1 out of 6. And I should be more specific with that, right? This is simple probability, right? Simple. This is easy as it gets right here. Looking at some of that. Can we spice it up a little bit though?
Yeah, let's make it a 20-sided D&D die.
Mr. Roy,
Because we really hate
is it
ourselves here.
the probability of it happening once and then use whatever amount of times it's asking? Can you just take it to the power of that?
Can you just do what?
Do you take it to the power of that?
What do you mean to the power of that? Keep
Well,
talking.
Like, okay, so for the coin example, it was 1 over 2, so there was 2 possible ways for the first time, right? And then there was 3, you were doing it 3 times, so you took it 2 to the power of 3 equals 8. So it's 1 over 8.
If they're all the same each time, right? If each
Right,
number
yeah,
of outcomes
yeah.
is the same, that'd be true.
Okay.
Yeah, I get what you're saying. Yes, that would be true if they're all the same. Now, here's where it gets kind of crazy though. This is where I want you to focus at here. I'm kind of jumping deep now into it. Not that we're trying to promote poker in school here, right? But this is a great way where you see probability come into play here, right? I think Mr. Wissing, they do a little bit of this in data analysis. Now, if you don't, who does not play cards? Let's be honest with you, don't play cards. Like I grew up, this is what we do at every Thanksgiving, Christmas, anytime any relative ever showed up to our house, we all sat around the table and play cards. Like this is my life. But not that we play poker necessarily, but a standard deck of cards, 52 cards. That means no jokers here, right? So 52 cards, no jokers. Maybe you should go through there. How many suits do you have in the deck of cards? You have 4 suits. What are the 4 suits? Diamonds, hearts, spades, clubs. 4 suits. 2 of them are red, diamonds and hearts. 2 of them are black, spades and clubs, right? We know these things. You have the ace all the way up to the 10, right? And then you have how many face cards? 3, the jack, the queens, and the king. So you have how many cards in each suit?
4.
13.
You have 13 cards in each suit,
oh,
right? So ace all the way up to 10, there's 10 of them. And then you also have then the 3 here, the jack, king, and queens, right? Face cards are considered the jack, queens, and kings. So what's the probability that none of the 5 cards is a face card? So, but here's the thing though, you're being dealt what? How many cards here?
5.
I got 5 cards in my hand. So again, what's probability? This is about as tough as it gets. We'll go back it down from this, but I want you to see the extreme here. If I want to find probability again, probability is the number of successes What are your thoughts here? I'm gonna lead you down this road right now just to see where you at on this, right? Instead of flipping a coin, that's easy. 1 out of 2, Mr. Ray.
I have an answer.
I have an answer too.
I have an answer too. The problem is my calculator does not put it in fractions. It only gives me That's a
Well,
shame.
now it's not gonna give you. No, if you want to fix that too, if you go to math and just hit the bracket button right here and then enter,
No, mine doesn't do that.
it should do it.
It should, but it doesn't.
Well,
It should. Sometimes if it's not
5 sections.
A nice round number. Should this should be it? Well, no, not necessarily.
That's 40 that aren't facing.
Anybody thoughts how to come up with this? Oh.
There's 40 chances.
But you get there.
5 times.
Help me out. I know you're multitasking. Jeez, I know.
Stuff like that.
We'll be done though shortly. Yeah, fine. You may know what I'm doing here. 10 minutes.
Yeah, 3 over 30.
Take a few minutes here. There's a lot of things to do this.
Okay, so, like I took,
Coach, man.
there's 4 of you.
You have 4.
Well, no, because
So there's 4.
it's 4. What are the odds of 5 face cards?
So they say the probability that none of the 5 cards is a face card.
Right. So you
So-
take all the face cards out first, right?
So how many cards are face cards?
Well, yeah.
So,
You subtract them.
so if I want to find the number of the number of not to have face cards, right? The probability of not having
There's
face
40
cards.
non-face cards.
There's 40 non-face cards. True?
True.
So there's 40 cards that are non-face cards. That's a true statement.
Yeah.
So taking out 3 of each of them, all 4 suits. What about should we go with the total here? How do we get the total?
Well, it's 50. Well, it's 52 times 52 times 52 times 52.
Well, but if I'm dealt a card though, right? Then it's gonna be, instead of 52, it's gonna be the next one 51, which is then gonna be 50, right? And then 49, 48. What's that actually? That's actually something you already know.
Permutation.
That's a permutation. Well,
Well.
No way. Wow, bro, that's crazy.
I gotta be careful how I say this though, because the way you're thinking of it right now, that would be kind of true. It looked like a permutation.
It would.
It doesn't matter though what order I get dealt these cards though, true? It doesn't matter that the first card is, right, when I get the cards, it doesn't matter which one's first, second, third when I play in the hand of poker. I just have 5
Yeah,
cards.
but it's not, it's combination something of, it'd have to cancel, the bottom would have to cancel out a lot of cards, because it wouldn't be 52 factorial on the bottom.
How do you get this? How do you get the top? How do you get the bottom, the total number of cards then? You have how many cards total?
52 times
52 possible cards. But again, do I care about the order that I'm getting dealt in? No. So this is called a combination. Right? This is again, and how many cards am I being dealt?
5.
This would tell you the total possible ways to get 5 cards out of 52. The question here though is, we just want what though? You told me this already. You just want the non-face cards. Bless you.
So 40 combination?
So in our case, to find out, how do I find these non-face cards, these 40 cards, it's gonna be 40 combination 5 again, because I don't care what order I get these 5 cards. But this is again a place where I'm counting here now, right? So I'm counting, but I'm using this now as a probability where I'm finding my successes. I want 5 out of these 40 non-face cards out of the total, 5 out of the 52. That's gonna create my probability for me. This is a big number, right? I think if you type this in your calculator, I don't know. This is what I got at one time. I think I wrote this down right.
Error domain, it's too big for my calculator.
That's what I got.
Which means it goes over the,
Which means you do it.
I get this fraction here. This fraction again, if I reduce it, it's gonna be a number between 0 and 1. My calculator though, if this is what I got here on my calculator, if I take this divided by this, it might tell me as a decimal. Yes?
0.2532.
The way you get around this, if again with these graphing calculators, how you actually write a fraction. If this is whatever decimal this might be, if I go to math and hit frac, so math in the very first button should be frac, F-R-A-C, hit enter again, it should reduce your fraction for you. And I can show you this if you want to see this. The reduced fraction, you get this on your calculator? 2,109 over 8,330.
You make it more useless around here.
Again, but that's at least a reduced number, and it's a fraction, but that would be my probability. And again, this number is between 1 and, or 0 and 1. What might be? So how do I do that? Let's quick take a peek here. Calculator, hop up here, because this will be useful today. Now, we'll go back and do some simpler ones here. Mode, let's quit this. So if I did, what was the first one? NPR, or NCR, and we had 40 combination 5, right? And I'm dividing this whole thing by, I'm just gonna type it in here, math. 52, combination 5. I'll put this in parentheses. This should work here. If I hit enter, that's my decimal, right? It's like a 25% chance of it happening. Now, if that's my decimal, what is that as a reduced fraction? If you go to math right here, so I just hit math, and the very first thing that pops up is this frac. If I hit enter, and then hit enter again, it'll take your answer and write it as a fraction. It always will write it in the reduced form, if it's possible.
if it comes out as a,
If it comes out as a nice fraction. So if you might have numbers sometimes that don't work out to be written as a fraction, then it'll leave it as a decimal.
And then do you want us to leave it as a decimal, or do you want it
That's fine,
to
if
be
it
a
won't
percentage,
reduce,
not a percent,
yeah.
not a percent?
But this is a lot faster than dividing by 2 and on and on and on, breaking this number down. That would take forever, but using your calculator to reduce it. That make sense? You think you do that? Keep going, Mr. Roy. Now here's some ins and outs though. This is the part, this is at least the piece I want us to get here. in the world of probability, there's something called intersection of events. In notation, I don't know if you're familiar with any of this notation. So this is if you have two events, A and B happening, and the intersection is an and event. This is what it could look like. So what's the probability of event A and event B happening? If it's an and event, when they use the words the probability of this and this happening, we saw this the other day. I don't know, do you see what form of math you're doing right here? What am I doing with each probability? I'm multiplying. So when you have multiple probabilities, multiple events, I should say, if they use the word and this goes back to the ACT, for instance, you see a lot of these things and keywords here to look for. Something and something else happening. These are what they call intersection of events, but I want to multiply find each one and multiply them out. And what I'm really looking for is the overlap between these two is what it's actually finding for me of where these things happen. So if my events are independent, so what's the probability that I roll a 4 on my die and get a head on my flip? Does rolling my die and flipping a head on my coin, do those two things have any effect on each other? They're completely independent of each other. Like rolling a die does not affect me flipping a coin, right? The two things are completely separate events, so they call these independent events. If though, this case, if they're dependent to each other, it's still the probability of A and B, and this looks weird as it's written, but it's the probability of the first event times, again multiplying the probability of event B dependent upon event A. So can you think of something like two events where the one affects the other one? So if I had a bag of marbles, go to the marbles here, right? I reach my hand in the bag of marbles, what's the probability of getting a green one? Well, if there's 3 green ones out of the 10, the probability of getting a green one, 3 out of 10. But what's the probability of getting a green one and another green one? Well, if I pull a green one out of the hat the first time, the bag the first time, my next probability of getting a green one again, if there's going to be one less marble in the bag and even one less green one in the bag, it affected the outcome of my next event. Does that make sense? So the probability of getting a second green one would be, let's say, 2 out of 9 then, because there's one less marble, one less green one. So anytime the event affects the other event, it's dependence. But still though, if you have something and something else, this is what I want you to remember, or at least write down.
Okay.
And means multiply. Oh.
So I'm just guessing this. So if A is a fraction,
The probability of A is a fraction.
the probability of A is a fraction.
Yep.
Because of skip, flip, multiply, that would mean that the odds would be larger than if they happened.
Now these are just, well, this is for multiple events here, right? So we're not
Yeah.
saying, hey, what's the odds of the Cubs winning the World Series, right? We're just saying, and that's just one event. We're saying multiple events. What's the probability
Well,
of
I know, but it would
this
be larger than
and this
if a
happening?
single event would occur, which is counter, like,
Probably true.
yeah, like that doesn't make any sense.
But odds, don't even deal with odds though. Odds is really just one event. What are the odds of this one event happening? We don't
I
talk
know.
about the odds of multiple events happening like this though. So this whole skip, flip, multiply, I won't have to worry about that because I'm not gonna have the odds are just for one event. And so what's different about this is now, that's like just saying the probability of event A happening, or the odds of event A happening, but now we're talking about multiple events happening, the probability of.
I know, but if A is a fraction, it would be more likely to be more likely for 2 events to happen in sequence than if they were in a vacuum. It doesn't make any sense.
Patience here. We'll see more examples. So I think you're going down a road that I think is going to make you more confused with where you need to be. So patience here with it though. Now and means what?
Multiply.
Keep going, Mr. Roy. 2 other ones here. A union is the other one. A union looks like this. A U B. That's how they write this fancy notation for union. But these are or events. When you see the word or means not multiply, but or means addition. So the probability of me rolling a 4 on my die, or getting a head on my flipping a coin, this means the or is telling me I need to add my events together. And really what this is saying is you're finding everything here is what you're finding. So the event A and event B, you're not finding the intersection, you're finding the union of them, you're finding everything. And so again, like ACT and stuff, you'll see questions like this. Probability of this event, or means adding. I mean, this is kind of, again, the trick there. Now, if they're mutually exclusive, those are two big words. Help me out. I'm not an English person, but exclusive means what?
You can't have one without the other.
So if people are exclusive, then what's that mean? Well, what's the opposite of that, I guess? The opposite of that is non-mutually exclusive. So exclusive, I should say non-mutually exclusive, I do the same thing. I add each probability up. This one's kind of specific here. I add each one up, and so the probability of event A and the probability of event B, but I have to subtract, though, anything that overlaps between them. So if the two events share something in common, we have to subtract that from there. Let me think of examples here.
I don't know.
In a deck of cards, what's the probability of getting an ace or getting a spade? Those two events would be non-mutually exclusive in the fact of there's going to be an overlap of events. There's how many aces in a deck of cards? 4 out of the 52, so that's the probability of getting an ace. The probability of getting a spade, though, there's how many spades in the deck of cards? 13 of them. The only problem with those two events, though, is they both shared what, though? They both shared the ace of spades. So you're counting the ace of spades for the first one. That was one of the 4 of 52. The other one, I'm counting the ace of spades again because it's a spade. And so I have to subtract that one card that overlaps in that case from there to find my total probability since those events overlapped with each other.
And it's the one part of the 1 over 52.
The 1 over 52, that probability of that event happening, what it might be. And so as I look at this, sometimes I have or events, I need to make sure that they are exclusive, means they have no connection with each other. That's what exclusive, right? They have nothing in common with each other. It's like saying they're independent, and that's why they use these big words. One event is not affected by the other one, nothing in common. So, nothing in common. Those are the easy ones. Whereas non-mutually exclusive just means they are going to have something in common. I have to subtract that common piece there. But this, though, you've probably seen this before, yes? So if anything you picked up today, or means, and means, if there's anything you learned today, please learn that, at least that, right? So at least say that. One last one, though. Last one, and then we'll look at some problems, and I'll call it a day. Sometimes it's easier to look at the complement of an event. Have you heard of a complement before?
Mr. Roy, you look nice.
Grayson, that's a nice blue shirt you have on there. Much better than the St. Louis shirts that you wear sometimes. So thank you for anyway. So a complement, though, in the world of probability, though, is the probability that the event will not happen. So it's the opposite of what you want in some ways. They use this notation. They use A prime right here. That's the symbol for a complement. So if I said the probability of event A not happening, the complement of A, well, all you have to do is find the probability of A happening and subtract it from 1. And that should give you all the cases where A is not going to happen. Since 1 is the most it could be, 100% guaranteed. So the probability not A, or again, they would write it as A with a little tick mark here. You're just taking that probability, subtracting it from 1, and that finds everything else, right? So everything that's not A, that's its complement. Sometimes it's easier to find the complement of something as a way around some of these pieces. So here's what I want to throw your way, though. Again, this doesn't come up really, and or is really what I want you to see, but can I throw out some examples your way just to see how you would handle it? I'm going to use a lot of cards here, and some quarters here, and some. But if I threw some of these out, do you feel like you could find these probabilities? Ready to do this? You got people to work with, you can talk to here, yes? Here they are. Let's go some cards. Standard deck of cards, 52 cards. What's the probability of choosing 2 black cards from a standard deck of playing cards without replacing the first card, right? So I pick a card out, I don't replace it. What's the probability that it's going to be a black card and a black card? And again, when I interpret this though, right, even though it doesn't say this though, this is like saying probability of doing what though? How many events do I have? 2 events, but even though they don't say it, it's probability of getting a black card and the black card, right? So it's probability of getting black and another black one. That's what I'm looking for. So what do you think? And again, I'm not replacing it, so I pull out that card, assuming it's a black card. How's that affect the next outcome? So talk with each other. See if you agree.
It is at 52C probability.
So do each probability. So this again,
Yeah,
what's
that's what we're struggling with.
what's and mean though?
Multiply.
Multiply.
That's not what
So
we're struggling with.
that's not what you're struggling with. So if I said what's the probability of a black card?
26.
I'm gonna multiply.
26 different options.
So 1/2 shows 1/2.
So I just did this one event. How do I get 1 black card? 26 out of 52, or some of you are saying that's the same thing as 1/2. I'm going to multiply, but now again, if I'm not going to replace it though, what's this now? This is dependent. It changed now. My next one's going to be because again, this changed because I assume I didn't replace it.
Said without replacing.
So if you take the card out, then you only have 25.
Now, if I did replace it, if it said replacing the first card, then again it would be the same thing. It'd be 26 out of 52. But since I didn't replace it, there's 1 less black card in the deck, 1 less card in the deck. Now, if you multiply this out again, calculator, how do you multiply? Top times top, bottom times bottom. I think this comes out to be like 650 over.
2,652.
Now, I would ask though, I would expect the reduced form of this reduces, so if I want to use my calculator, if I type that in and enter it's a decimal, hit that math back button, or that's the same thing as, what is it, 25 over 102. And maybe some of you at the very beginning said, hey, this is 1/2, so you change that to 1/2. If I multiply 1 times 25, I get 25, 2 times 51 is 102. But I'm just finding the probability of each event individually, multiply out. Sure? Keep rolling. Change it up here, Mr. Lake. I want to get 2 black cards and 1 red card. And I'm going to replace the cards drawn each time. How's that change things? So how many events this time? So 3 events. So probability of getting black. Would it be and or here? And so black and red.
Wait a second. All right. I have a question. If it was the probability of choosing 1 black card, well, no, that would make sense. I still want to know how we get the the P divided by A, if it's like 1/2 divided by 1/2, how we have the odds of something happening 100% of the time, even though the previous,
But we're not,
even though event A
we're not
was
finding
only
the odds, though.
50%.
We're not finding the odds, though. So that's where your odds again are just for one event here. Now,
Sorry,
probability we're
the
finding
chance,
multiple.
still, the chance would be 100% of it happening, even though the first dependent would only be a 50% chance of happening.
Come back. We'll come back here on.
That doesn't make
tight.
sense.
Hang tight. I wanna investigate more of your thoughts here. I wanna get through everyone else's time here.
Oh, wait. Are you talking about the part where it's like A and then a line and then B?
Yeah.
That's not dividing.
That's not divided.
It's not dividing?
No, that's just special notation. It's just that
It's
notation.
said underneath it.
Back it up, Mr. Ray. Right here.
Back it up even more.
No, back it up, right here, this guy right here. This is just special notation, this, not divide by, but this is how they write this though. The probability B dependent upon A, that's what this is saying, the probability B depending upon A is the number of ways B's can
That's why I
happen
wanted it.
after the
That's why I
event
was
A.
confused.
Okay, that's, I was trying to understand what you were
I
trying to say.
thought that
but-
was divide. I didn't think, that was multiply.
It's not divide, it's just it's this notation that they use, it just says B depends upon what happened to A, so. Like the last example,
That's why I was confused, because that shouldn't be like that.
what do we get here though? Keep rolling. So probability of getting, again, black, and red, right, is what we're saying. What's the probability of black one? 1/2. You want to go 1/2? That's fine, 1/2. What's the probability of another black one? 1/2 again. And what's the probability of the red one? Why are these all 1/2? Right, so my answer would be 1 out of. And again, if it wasn't replacing, what would it be if it was non-replacing?
Not a pretty number. That's all we know.
What if it was no replacement? Just so the first one's gonna be what? No replacement is gonna be 1/2 for the first one, but what's the second one then? 25 over 51, and then the next one would be good. The next one, because it's the red one, you assume you have all red ones left there, right? Because I didn't take them out, but then you're only gonna have 50, right? If you didn't replace it, does that make sense though? The first one's 26 out of 52. The next one, I took out that black card, so there's only 25 black cards out of the 51. But then the third one, the red one though, there's still all 26 red ones left out of the 50. That's how I'd have to do it if I didn't replace it. And I don't know what that would be, but keep going. More cards. Nickels, dimes, quarters. I know, this is why we're not spending a ton of time here with it, but I'm not trying to make your life miserable. Not
Imagine
trying.
if you gave us a question and be like, calculate the number of scenarios that would get you to equal X number of cents. Like, put the coins together. That'd be
Not
really,
going.
That'd be really cool.
So you have a bag of pennies, 13 pennies, 8 nickels, 12 dimes, 7 quarters. If you select one coin at random, right? I'm just close my eyes, reaching in the bag, not knowing the difference between a penny and a dime, I guess. What's the probability that it will be a penny or a quarter? Keyword though is what? What's the keyword?
Or.
Good. Again, ACT, this is the second question on the ACT. I mean, this is the difficulty of it though. Or again, is telling me it's gonna be adding.
So there's 40 total coins.
There are a bunch.
40 total, is that what we're saying?
Yeah.
That matters, right? I need to have my total. So how do you find pennies though?
There's 13 pennies out of 40 total.
13 out of 40. Or again, you told me is add, so we add. Quarters though, there's what?
7.
Now does this, are quarters affected by my pennies though?
No.
Is a quarter the same as a penny? Like no, so because these are completely mutually exclusive, they don't depend upon each other, then this is just gonna end up being, you said 7 out of, if I add these up, what do I get? Does that make sense though? Why is my answer 1/2? Because half of the coins are pennies and quarters, so the probability of getting a penny or a quarter is 1/2. That's kind of like what an OR question would like look like. Awesome, appreciate it. Dos mas, you guys got it.
Really? I thought it was more. I haven't been there since freshman.
You guys we're wearing it. Look at us. Oh, look at us. getting tired, sleepy. We're wearing out here. I know there's lots of examples. So 52 cards again. Probability of getting dealt a queen or a face card. Oh no.
It's mutually exclusive. It's non-mutually exclusive.
Do queens and face cards have any overlappage?
Yes.
Anything that they could be the same. So how would I figure it out in probability of?
Well, it's not too bad, 'cause it's just,
This isn't too bad.
but it's still. Probably. Well, now we just have to figure out what the probability of getting a face card is. And that's 12 over 52. And minus 4 over 2, so that's 8 over 52, which.
Again, I'm gonna keep saying this, not to make this repetitive, but the word or again that's a signal that I'm doing what here? Adding. So again, probability I'm getting a queen or face card.
Oh my goodness.
So we already made this into a big deal. What are we coming up with? What are you thinking? Why does that reduce it all or not?
No.
It doesn't. 4 over 13. If I said no to that, Anna's thinking 2 over 13. We're so
What do you
close.
think?
No. 3 over what? 3 over 13? 3 over 13 is what we want.
That's what I got.
3 over 13? We won 3 over 13. How do we get 3 over 13 out of this? How many queens are on my deck?
4.
There's 4 queens in the deck, so there's gonna be 4 out of 52, or that's the same thing as 1 out of 13. We can reduce now. Or means we're gonna add. What's the probability of getting a face card?
12 over
We'll still have
52.
And again, why face cards? Why is it 12? Because you have
Yeah.
I love how
Three
they're just
per
giving
suit.
more and more of a roster. They're like, yep. this
Owen.
guy's-
Owen,
What? Sorry.
thank you.
I mean, I have the answer. I didn't.
Now, if I did this though, what's wrong with just doing this though?
Isn't this one of
They're
those
overlapping.
It's an overlap.
There's overlappage, so I have to keep that in account. I'm gonna have to subtract from this whole thing what overlaps here. What did I already count here and counted it here as well? I counted what card is both a queen and a face card.
4 of the queens.
There's 4 queens they're all face cards, right?
Yes. you
So
get-
technically I have to subtract the.
So just leave the 12 over 52.
So what's my answer come out to be? I mean, ultimately, what ends up happening?
You just simplify 12 over 52.
There's 4 queen / face cards, so that's why I'm subtracting that overlap. And so what do I ultimately end up with? I just end up with 12 out of 52, or reduced is 3 out of 13. So I just have to be aware, certain cases, again, this is where there's non-mutually exclusive, where that comes out to be there. But subtract anything that would be counted here and counted here. This one, they're all counted. Again, so really, this is just asking how many face cards, is really what it's saying, because they're the same thing. Good, should I stop here?
Yeah.
Is this, I don't know, now, before you get mad at Mr. Roy, don't get mad here and stuff, you're gonna see, some of these questions, I try to pick out doable ones, we're not going deep into all of this and stuff. So it looks like a lot, but I'm trying to pick out ones that I thought were doable for us to do without making it more complicated, so this is kind of for our benefit here. I think 7 and 8, you might have to draw out a little sample space, like look at all the possible outcomes. But then the rest of them, I just want to see then, find the probability for most of these of events happening. Tomorrow we're going to come back and we're going to, really tomorrow I'll just go back and overview of a lot of the things, a couple different activities to practice, some counting again, combinations, permutations, some of those special permutations, even some of this probability stuff. But again, keys of the day though is and means multiply, or means add. Now, if Mr. Roy can do this.